All right, so it's a great pleasure and honor to have Professor Conway with us today. And he agreed to come to class. I talked to him that one of the topics in the class is protein folding, and he said, I don't have anything to talk about. So I said, we're going to just have a discussion about themes that would be, let's say, mathematical foundations for questions in mathematics that have relevance, because if you don't understand those, you cannot make progress to the next level, or at least that's how we think.
Okay, so I don't understand those.
But how about something very simple like sphere packing? Simple compared with...
Yeah, well, very simple. I got involved in sphere packing. I don't suppose much of what I did will be terribly interesting to you, because it's usually with respect to very high dimensions. So, I worked on this packing of spheres in 24-dimensional space, which has actually recently been proved within the last year or so to be within 1 part in 10 to the 33 of the best density you can get in 24 dimensions. Funnily enough, you can only hope to answer these questions in 1, 2, 3, 8, and 24 dimensions, for reasons I don't understand at all. But I got very interested in the sphere packing problem and wrote a book with a friend of mine called Neil Sloan. He likes to work, and I don't really like to work, so he did most of the actual writing on the sphere packing problem. Yes, I don't know what to say about that. Then more recently, by the way, I worked with Sal Torquato. You know it, I believe. Or don't you?
Who?
Sal Torquato? No. I thought we had a common acquaintance there. He's interested in packing other things, and we wondered, just as a sort of sample problem, about packing the regular polyhedra. Now, cubes are easy to pack. You can get density 1 with cubes. We answered these questions for everything except the simplest regular polyhedron, the tetrahedron. And there, you can get a density of about 75%. But it's not at all clear that, the packings we know. There was a young Chinese-American lady, Beth Chen, who found what is currently the record for that. What was I going to say? I had a brilliant idea a moment ago, and it's just vanished. It'll come back.
So it's a similar phenomenon only for some type of polyhedra you can find the density?
Well, you can't answer any questions here. I mean, the simplest question of all, roughly speaking, is, how densely can you pack spheres in 3-dimensional space subject to no other constraints? And there, Kepler, who's a hero of mine, by the way, Kepler guessed the answer in 1613. And then Newton and Gregory had a bit of a discussion about it. They had a discussion about the kissing number problem. How many spheres can touch a given one? Kiss, is a billiards term, but it's also rather nice. Some of us like kissing. How many spheres can touch a given one of the same size? The answer there was only found in the 20th century by my friend John Leach, although again it was guessed before, and a hand-waving-y sort of proof was given in the 19th century. So it's often said that this was proved by so-and-so, but it wasn't really. The answer is 12. The thing about packing 12 spheres around a given one is they're actually quite loose. I proved a nice little theorem. Suppose your 12 spheres are numbered 1 to 12, And you think of it like the 15 puzzle, if you know that. You can slide little blocks around and get different orderings. I proved with a friend of mine that taking 12 spheres touching a given one, you can achieve any permutation of those 12 spheres while keeping them always touching the center, you know. So you sort of roll them round and you can get, that's a good idea of how loose it is.
So I don't understand the result. Can you just randomly rename them in any permutation?
Well, no, what you can do, you know, you can, here they are, 1 is here, 2 is here, 3 is here, and so on. And now I can roll number 2 to where number 1 was, and roll number 7 to where number 2 was, and so on. Keeping them all touching the central sphere and never overlapping each other. There's a funny thing about that. You can get half the permutations without, let's call the 12 spheres the planets, because they're sort of rolling around the sun. You can get half the permutations, even if the planets are slightly bigger than the sun. There's extra space, you know. I don't know whether you can get all permutations if they're the same. I mean, if they're slightly bigger. You certainly can if they're exactly the same size, but on the way they sort of graze each other, if you understand what I mean. That's that. Say something else.
All right, so do you understand why the proof, first of all, Hale was a student?
Hales.
Yes? Hales, or he, of course.
In a way.
For me the problem, or what was this?
In a way, yes. I don't know, because I didn't know I'd inspired him, so to speak. Yes, so I don't know whether any of you know the history of this. Kepler wrote a little book dedicated to his patron, the something of something, in which the six-fingered snowflake, it's called. And he talks about many things in there, not just snowflakes, but in particular, he wonders how well you can pack spheres in 3 dimensions, and came up with the answer, which is the standard way you used to see, I haven't seen them for some time, oranges stacked at the greengrocers and so on. It's not sort of unusual, and there's some variations of it which are interesting. But that was only conjectured to be the best possible density. Roughly speaking, there's a statement somewhere that, what is it? Many mathematicians believe, and all physicists know, that the answer is such and such, you know. Well, we all believed it, but we didn't know. This gave rise to some problems. There was this man, Wu Yi Shang, who was a brother of one of my colleagues at Princeton, actually, Wu Chung Shang, who announced he had a proof, and, you know, he didn't really. I don't want to animadvert on that too much, but well, maybe I'll tell a story, as long as you promise not to repeat it in too much detail outside this room. So I wrote this book with Neil Sloan, and we also wrote some papers just on the sphere packing problem. And one time we got this preprint from Shang announcing a solution to the Kepler problem. And and by the way, before that happened, Shang came and gave a lecture on his solution at Princeton. And I sort of basically believed him then, that he had a solution. A proof that the solution was optimal. There was, however, one funny little thing which later on I wondered about, which is he defined in this lecture a notion of close neighborhood. Okay, a sphere was a close neighbor of some other sphere if some condition and some other condition and some other condition. And I didn't quite understand this, and I sort of put my hand up hesitantly and said, So it seems that A can be a close neighbour of B without B being a close neighbour of A. Is that the case? You know, have I understood it correctly? And he said, yes, that's true. I mean, it's an asymmetric relation. And then he proved a theorem that a sphere could have at most 12 close neighbours. But then he went on to deduce some consequence of that. But what he seemed to be using was that a sphere could be a close neighbour of at most 12 spheres. In other words, it would be the same if the relationship was symmetric. And again, I put my hand up and I said, isn't this the interchange of what you had or something? I can't remember. I was very hesitant because I wasn't really listening terribly much. And I wasn't quite sure that, you know, I had got something wrong, you know. And basically he said, no, I think you'll find, you know, if you think about it, I've got it the right way around. So I shut up. And then next morning I saw him, and in fact I think I said we must discuss this tomorrow morning, but I think I was right, you know. And next morning he came and he said, oh, I'm so sorry, you were quite right. I originally had a symmetrical relationship, but I found I could cut 10 pages off the proof by making it asymmetrical, and I didn't quite get it right. Well, I believed him, you know. But it was a sort of funny thing, you know, in memory. But then it turned out, when we got his preprint, I looked at lemma 1, and lemma 1 had something wrong with it. Basically, it used the fact that we had three spheres whose contact points formed a spherical triangle with a given sphere in the middle. And so the edges of this spherical triangle were at least such and such, because otherwise the spheres would overlap. And he worked out the area on the assumption that there were exactly this much, and then used that to get some inequality, that at most 12 spheres or something, I don't know what it was. But he made use of the principle that if you have a triangle and you increase all its edge lengths, then you increase its area. That principle is false. You know, if you have a triangle whose edges are 1, 1, and 1, you increase them all, say to 2, 2, and 4, and now the area is 0. But I wasn't quite sure. Maybe in context, you know, if you added some other condition, which he would probably tell me, you know. Anyway, there was something wrong with lemma 1. But it wasn't obvious it was really wrong. And then there was something wrong with lemma 2. And then there was something wrong with lemma 3. And I said to Neil, I don't want to read lemma 4, nor anything else by this author, I said. It's a sign of how touchy the problem was, actually. Well, maybe I should cease animadverting on Zhang's proof. It's not generally accepted now. I mean, he worked through it. He made these lemmas correct. You know, they could be patched. But roughly speaking, if you find simple things wrong with lemmas 1, 2, and 3, you don't believe anything is true about lemma 47. You know, I mean, it's so hard. And fortunately, this problem was attacked by this other mathematician, Tom Hales, who wrote in a totally different style, and everything was as tight as you could possibly imagine. But, you know, the problem lasted from 1613 to 1990 something. Yes. And it's just terribly hard. You know, it's a mixture of inequalities and combinatorics. Any of these problems, if you want a solution to satisfy a mathematician, you probably don't. But I mean, if you want a solution to satisfy a mathematician, you're not going to get one, roughly speaking. They're just too hard for us at the present state of development.
So by saying combinatorics and inequalities, you mean continuous math and discrete math at the same
mixed,
time?
yeah.
It's very similar to protein folding.
Yeah, no, you're not going to get any solutions, you know. Well, I mean, but no, but I mean, I don't think that's wrong, you know, bad or anything.
So
I mean,
so
it's the question.
ready for such results yet?
Well, yes,
The
if you
21st
actually,
century?
if you actually want, you know, provable results, the sphere packing problem is, you know, it stands as a sort of awful warning. You know, here's a problem posed in 1613. The answer is actually quite simple, but the proof was hell. You know, so in this kind, if you make it more complicated than that in some way, you just add another few centuries onto the expected, you know, proof date. And I'm not interested in things that are only going to be established in 2300, you know.
Could there be concepts of approximation that for which the proofs might be easier and still kind of do the job in the sense of...
Well, you do it.
Yeah.
No, I mean, I don't think there's anything wrong with this. You recognize what kind of problem you're dealing with and what kind of answer you're prepared to accept. You know, and if you demand an answer at the mathematical level, you know, total proof, well, it's just rather unwise. I mean, it's no good. You can ask for the moon, you know, you won't get it. So, you know, what happens? I mean, these problems in packing other kinds of polyhedra that I was speaking of, you know, we never bothered to sort of ask for proofs, except for the cube. For the cube, it's easy. But I am absolutely sure, for instance, that we have the densest packing for the regular dodecahedron and for the regular octahedron. So that's three of them. Then there's the icosahedron. I'm not quite so sure we have the best packing there, but we probably do. And then for the tetrahedron, no. But even in those cases where I say I'm absolutely sure, can you prove it? No idea. You know, and I don't expect to see one before I die. I'm not interested in the proofs that come out after I die.
Well, isn't Ramanujan...
I'm interested in the answers. Yeah, go.
You know, Ramanujan,
yeah.
You know, he had some infinite series for which nobody could prove them, but he had his...
yeah, but that's a different thing, though, because that was in a sort of well-traversed area of mathematics, and it was reasonable to expect proofs, and we got proofs in the end. These sort of combinatorial and geometrical problems, you know, the sphere packing one should be the easiest in some sense, and it took, what is it, 1613 to 1990, something like 370 years roughly.
And a dream team of people working on it.
Yeah. You know, I always thought, I thought when Shang was talking about it, that why waste your time doing it? Because the payoff isn't large enough. You know, you could work for a long time and prove this, but, well, is Tom Hales famous?
Well, the latest comment on his proof is that scientists believe that the proof is 99% correct.
Yeah, but that's nonsense. I mean, that's a terrible thing, by the way, which is Shang's influence. Let me just tell you that. When Hales came up with his proof, which he involved computer splitting of the thing into 2,000 cases, roughly, and in each case you had to verify certain inequalities, and these he was and by the way, I should say Hales and Ferguson, his student, he was tremendously careful. So, you know, you had an inequality. It was usually an inequality in several variables, but let's suppose it's an inequality in one variable. And so you've got to prove that for all numbers between 0 and 1, f of x is less than g of x, you know. And what he did basically was to divide the interval into 100 subintervals and then get estimates for the derivative, upper and lower bounds for the derivative, so that now you had these 2 points 100th of a unit apart, and the derivative here is known and the derivative here is known, so the function lies between something and something. And all the arithmetic was done with interval arithmetic, which is so that you can get precise things. It wasn't just up to so many places of decimals and so on. Astonishingly tight. It stands as a monument to that kind of proof. But unfortunately, Sheng tried to raise doubts about it at all times. The effect has been a bit pernicious. I know I had a heart attack a few years ago, and the Annals of Math at Princeton was about to publish Hales's paper, and I had just got out of hospital, and I telephoned the editor and said, I'd like to come in and make a presentation to you about this proof, because I had heard rumors about how they were dealing with it, and it didn't seem satisfactory to me. I didn't have any right to say that, but anyway. And I think they behaved very stupidly in a way. Namely, how can I say what? I'm trying to remember what happened. They got 2 teams of referees to attack it. Usually you send a paper to 1 referee. This time they sent it to 2 teams of referee. One of whom was sort of certifying the basic geometric method, and the other team was certifying the computations being used, and so on. And these teams reported various things, but they said, we have not checked every case. Well, you don't expect referees to check every case. I mean, the job of a referee is to assert, can it be proved this way? Is it likely that these authors have proved it, and so on? It's very foolish to imagine that the referees, when a thing has been split into 2,000 cases, the referees will check every case. After a time, you have to trust the honesty of the author. So, in the end, this paper was published with an editorial note describing this, and that editorial note, by the way, I sort of wanted to come and make a presentation because I heard of that. I wish I had. But the editorial note had the effect of casting doubt on it, because it says, the referees did not check every case, which sounds...
by definition a proof that is not humanly checkable.
Yeah, it was a ridiculous statement to make. There's no other proof like it in this respect. The previous analog was the proof of the 4-color theorem, which was done by computer checking of lots and lots of cases. That raised a lot of doubts, because what actually happened was the case tree was generated by hand, and lots of errors were found, but they were all in this hand part. But there was a lot of discussion at the time it came out that, if a proof is not humanly surveyable, is it a proof? But in this case, the part that was being discussed as if it were the new thing, the computer-generated part, it was the reliable part. The unreliable part was the part that the humans, took in. There's been a lot of nonsense talked about these sort of mechanical, machine-assisted proofs, let me say. But it looks, with problems like this, it looks as though we're going to be in this state for some time. There will be other theorems proved only by massive, interaction between humans and machines. And there hasn't yet evolved a satisfactory sort of protocol for them, I think.
So another concept that shows up in protein folding that has tremendous mathematical difficulty is self-avoiding walks. the backbone of the protein. This is also notorious. We cannot count them. We cannot find formulas even enumerating them. And all chemistry formalism needs somehow to model this. And
you can simulate something.
They say, probably we enforce it through constraints, and it's always hard.
But you know, every time you say the phrase protein folding, I go, well, so am I, knowing nothing about this subject.
Well, but we're talking about foundational questions related to it.
Yeah.
Sphere packing was. So have you worked at all with self-avoiding works? And,
a little bit.
Counting them, and why?
But don't ask me anything. Well, I mean, you have no right to imagine that a problem's going to be easy. Why should a problem be easy? Some problems are, and some problems aren't. And I don't see that, you need a reason why anything should be hard. You need, in fact, a reason why anything should be easy. Sorry.
You're turning more
Oh.
in the back of your head.
Okay. Oh, I'm sorry.
We want, maybe you can come.
Yeah. Okay.
If I get closer together, so I can hear.
Now listen, I was telling you some anecdotes before we
Let's
started.
hear some anecdotes. The von Neumann anecdotes.
Yeah, well, there are a few anecdotes about von Neumann. Von Neumann has been a sort of, a source of inspiration to me, and now I'm very proud to be the John von Neumann Professor at Cambridge, the John von Neumann Distinguished Professor, you see. Look at this, it's distinguished. But because I've never really done, I don't know, it's hard to say. I haven't got any ideas for how to do mathematics from von Neumann, roughly speaking. That's a true statement. But I have got a number of problems from von Neumann, and it's rather nice. I get invited to von Neumann type celebrations every now and then. And there was one in Hempstead, Long Island. And, let me tell you a nice anecdote about that. That was very funny. Von Neumann's daughter, Marina, came to tell us about life with Daddy. And she was a very self-assured woman, a very striking woman, especially since she was dressed in a red dress, and a very expensive-looking red dress, I may say. She was some kind of executive at General Motors. And she came supremely confident. It was one of those lecture rooms where the seats rose up to the sky, if you understand me, physics-type lecture room. She sat on the dais at the front, swinging her legs, and told us stories about life with Daddy. But the funny thing about this was next day we had Edward Teller, who had worked with von Neumann. And he did more or less the same thing, except that he wasn't dressed in a red dress. And he spoke about life with Johnny. And then the funny thing was, the peculiar thing was, at the end of Teller's talk, some sort of lowly graduate student raised his hand and said, "What can you tell us about von Neumann's children?" And Teller said, "There were no children." And to everyone in this audience had seen a child of von Neumann's, and they at least knew that this child existed, existed in a very strong sense in a red dress, and which I remember to this day, so it's quite striking. However, nobody said a thing, because it would have been so rude to say, "But we had von Neumann's daughter here yesterday." So there's a nice little anecdote for you.
She's coming in May. We have a big symposium. We have 2 days, von Neumann days. John is coming back, and von Neumann, Marina is going to open there.
Well, I met Marina again at another von Neumann celebration in Detroit. No, in Ann Arbor, near enough to Detroit. And I told her this story. I don't think she believed me, actually.
So
But
she wasn't the second day at the conference. She wasn't there when.
no, she wasn't there. She just came. You know, she was.
Just for the day.
You know, she had lots of things to do, and so she could only afford to spend one day. Teller only spent one day too. You know, but it was a rather funny thing. I had lunch with them, with Marina and her husband and George Dyson, who's Freeman Dyson's son, who I know quite well.
He's coming also, in May, as well as his father. Freeman is going to actually give a lecture on von Neumann.
Oh yeah.
He wrote recently in Notices. Did you see the bird and the frogs article?
I didn't see it. No.
Oh, it's a beautiful thing, and he talks a lot about von Neumann.
Yeah, he's a wonderful writer. I love what he says. But you know, how does anybody know of my life game here? The existence of it? A few of them. Okay. Well, let me tell you how I got that. Because this is one of those things that, in a sense, was inspired by von Neumann. There was a thing called automata studies or something. I think it appeared in the 50s.
Yes.
And I read this, and I think it was from there that I heard about this idea, you know, the cellular automaton. And this came from some discussions that von Neumann and a few friends were having, you know, in an informal sort of circumstances about colonizing the planets, basically. So they mathematized this. I think it was von Neumann himself who mathematized it. So you call this planet you're colonizing Mars, and we basically model it, it's an infinite plane, as far as we're concerned. And then this is divided into squares, and you mark in each square what resources it has in that square, you know. Lots of iron ore, probably, because that's what makes Mars red, and so on, you know. And then you send over a machine, and just one machine, clever machine. And this machine is supposed to be capable of building a copy of itself, or roughly a copy of itself, let's say, a copy of a machine rather like it. And so it starts off, it's a fairly big machine. It starts off smelting some of this iron ore that there is, that Mars is largely made of, and, you know, produces steel and things like this, and builds another machine. Okay, and now we've got two machines, and they both are working, so next time we'll have 4 machines and so on. And soon we've got a sort of whole army of machines all over the surface of Mars, busy humming away, producing more machines or something, except that they'll change into a new phase when, well, you know, what do you want them to do? I mean, they're programmed after, you know, you've built a reasonable density, maybe you start getting oxygen out of this iron oxide and building an atmosphere suitable for the humans that you're going to go there later, or whatever, you know. The basic idea is to build a self-reproducing automaton. And so von Neumann was faced with the problem of, can you do that? If you want to build a machine to build a copy of A, let's call this machine B. Does B have to be more complicated than A? You know, in which case you'll never get there, you know. But he proved with this notion of cellular automaton that no, it didn't have to be more complicated. And the basic idea is, in fact, you do what human genetics does. You have a tape which specifies the machine you're to build. And what the machine does is you give it a tape, you know, and it builds the machine specified on that tape. And if you can do that, then in particular you can make the thing build itself, because you sort of say, you work out the tape for the machine to do this, and then you feed that tape into the machine. You know, in other words, you feed its own tape. That's roughly speaking how we operate. You know, we have DNA, and it's complicated by sex, of course. So many things are, but you take the tape from your father and mother. But we only need to have a mother for this purpose, in fact. You know, she hands you some of her tape, essentially. It's very clever. And what happens with biology is so clever because it's in every cell of your body. You know, it's not just one tape somewhere, it's all over the place. The whole thing contains a recipe. So anyway, von Neumann eventually found he designed a cellular automaton. And I don't know whether you know what a cellular automaton is. Each square can be in one of finitely many states, and it operates usually with discrete time. So it can be in one of finitely many states at time t, and at time t plus 1, its state is found from the state of it and its neighbors at time t. And von Neumann built a system in which each square neighbored 4 other squares, could be in one of 29 states. So we have a function from 29 to the 5th to 29, if you understand me. There are 29 to the 5th possible states of this sort of cross-shaped thing of 5 squares. And he, in his paper at the back, this transition function is specified somehow by a lot of tables. I only saw this paper once. Then there's some argument, which I didn't read, to the effect that, you know, this is a self-reproducing automaton and so on.
Well, the construction is in his unfinished book.
Yeah, I don't know. I saw it in a typewritten version. I don't.
Yeah, there is building reliable components from unreliable.
No, that's in the building reliable out of unreliable is in the orange book. This thing isn't, and I don't honestly know where it was. But anyway, I sort of thought I had this idea. In many ways, it's not my idea only. I mean, all sorts of other people had this idea. I'm not claiming originality for it. That the thing to do was not to design your cellular automaton, but to find it. So you see, if you design it, then you want at some time the facility to do such and such a thing. You build it on. You add some states to do that thing, and then, you know, and then maybe you wanted the ability to transmit information across the plane. Well, you build a signaler, you know, and in this way, the number of states that you have to have in your machine rises, you know, and it came to be 29. Von Neumann did it pretty efficiently. He only needed 29. But I always thought that you should be able to do it with 2. In other words, on and off were the 2 states. And then you couldn't very well design something to be a universal. By the way, I'll use the word universal rather than self-reproducing in a moment, because the universality is in fact, in the sort of intended application, stronger than the self-reproducing. It'll build an arbitrary thing, in particular it'll build itself. But universal is the usual phrase for sort of computer ability, universal computation. So let me tell you my sort of dream for that. It is, you let me into a sort of electronics warehouse where things have been lying around since the 1950s, because I sort of understand the electronics of the 1950s roughly. There are various components, you know, resistors, capacitors, valves or tubes, as you said in this country, and so on, out of which you can build clever electronic machines. It's been mouldering there since the 1950s, though. And then, there was a madman who lived in it for a few years, and he just went soldering everything together at random, roughly speaking. And, you put a power supply in there. You might have to get one that hasn't been mouldering since the 1950s, so that it still works. And then you let me live in it. Here's this big machine with a whole lot of electronic components just soldered together at random. I believe in there you have the ability to do computation. I sort of dream of myself pressing this button here. Ooh, and a little light flashes over there. And I do it again, and then gradually I'm playing a sort of symphony with this machine. All sorts of lights are lighting. I suddenly discover I've found a way of adding, and so on. And basically, I believe that if you do connect a lot of electronic components together with virtual certainty, enough of them, with virtual certainty, you get a universal computer. And that's only one instance of the belief. The belief is, in general, make things at random with some kind of capacity, and then it'll be universal. And the life game was an attempt to prove this. And, in my life game, I just had the thing that I let the state of a cell, depend on the state of it and its 8 neighbours, the ones differing a king's move away. And the dependence is very simple. If it was dead at time t, or should I say empty at time t, it will be full at time t plus 1, if and only if it had 3 full neighbours, let me say live neighbours. And if, on the other hand, it was alive at t, it will survive, in other words, still be alive at time t plus 1, if and only if it had 2 or 3 neighbours. Those rules came as a result of lots of experimentation at coffee time in Cambridge on a Go board. We used to play with these things. And this set of rules eventually crystallized out because, well, the time we knew it had worked was wonderful. Richard Guy was visiting Cambridge at that time. Richard Guy, I had a telephone call from him 2 days ago. He's now 93. I should have reminded him of this thing. And he was given the job of looking after a small piece that didn't seem likely to be interfered with by the rest of the configuration for some time, so that he could just be on his own. He's a careful, precise man. We called this blinker watching, which was a slightly insulting term, but anyway. One time he said, "Come over here, I think my bit's walking." So we came over there. Oh, by the way, I should say, we did this thing on coffee tables, square coffee tables, with Go boards, and you could fit 16 Go boards onto one coffee table. And then you could call for more Go boards to be placed on the floor if it sort of went off the edge of the coffee table. So his bit was on the floor. He was fiddling around over here with it, he said, "Come over here, my bit's walking." So we came over there, and that turned out to be what we call the glider in the life game. We'd wanted one of these things. We called them spaceships before we found them. Before we found this one, spaceship is just something that moves across the plane, reconfiguring itself, So, and of course we wanted one of those because it would carry out the signaling possibility. And as soon as we found that, we knew, so to speak, that we had it made, or at least we strongly hoped we had it made. And I wrote off to Martin Gardner, with whom I was in fairly regular communication at the time, and told him about this. He got very excited. And I sort of advertised for what later turned out to be the glider gun. That's a thing that emits gliders every so often, which we needed in our attempt to simulate a computer. This was to be a pulse generator, a source of regular pulses. And I offered a $50 or $100 prize, I can't remember now. I think it turned out to be 50 in the end. But I didn't have to pay it anyway because there was some sort of legal reason why the Scientific American wouldn't let me pay. They paid, so fine. I didn't. I didn't object to that at all. And anyway, that started off a hair-raising thing. We actually proved that this life game was universal. I shouldn't perhaps be talking about the life game, but it was a very exciting time, and it was essentially suggested by von Neumann, so his name came into the act.
Well, protein folding is part of life
yeah, the trouble is, how can I say it? Well, I can't say I'm not interested, because I am interested, but I'm not interested as a mathematician. I can't sort of see any way in which, mathematical knowledge helps. I mean, computational ability doubtless helps. It helps in simulating stuff. Yeah, I don't know. I'm here on false pretenses.
So you said that von Neumann inspired you on several problems. What else?
Oh my, yes. Well, von Neumann, started off in mathematical logic. His thesis in the 20s was on mathematical logic and set theory. He had a very extravagant kind of set theory, but perhaps that would take us too far afield if I described that. But there's one particular thing, his definition of what are now called von Neumann ordinals, which, they're things like 0, 1, 2, 3, and so on. However, the and so on in that is rather longer than you might expect. After you've got 0, 1, 2, 3, ... you get omega, omega plus 1, omega plus 2, omega being the first infinite ordinal. And Cantor defined the ordinal numbers, or found the ordinal numbers, in the 1870s, but von Neumann did a very beautiful thing to Cantor's theory. The question is, what is 0? Well, von Neumann's answer was, we can take 0 to be the empty set. Okay, now what's 1? Well, von Neumann's answer is, you can take, it's the number after 0. But von Neumann's notion is that you can take for its definition the set consisting just of 0. In other words, the set, let me draw some curly brackets here, consisting just of the empty set. So what's 2? 2 is the set consisting of 0 and 1. 3 is the set consisting of 0, 1 and 2. That's von Neumann's definition of the ordinals. Oh yeah, I could. So, yeah, okay. Get one that works. I have to write left-handedly. I'm naturally right-handed, but I have to write left-handedly nowadays. So 0, oh sorry, and as you see, I'm not too good at it.
You asked me to find something that works, and I gave you the wrong one.
Okay. Well, this worked reasonably well. So 0 is the set consisting of nothing at all. It's got no members. 1 is the set consisting just of 0, which if we write it out in full is the set of the set. Well, anyway, it's just that. There's nothing at all in there. And then 2 is the set consisting of 0 and 1, which is the set consisting of the empty set and the set whose only member is the empty set. And then 3, well, it gets worse. This is a beautiful definition. It seems sort of slightly crazy, but if you want to count things, this is perfect. You see, 2 has 2 members, namely 0 and 1. And 5 has 5 members, namely 0, 1, 2, 3, and 4. And this definition continues to work past the finite. Omega is the set consisting of 0, 1, 2, ... all the finite numbers, and so on. That's the definition of von Neumann's ordinals. They're really Cantor's ordinals, but von Neumann's way of attaching a particular set to each ordinal is very, very beautiful. Well, I came up with a generalization of this notion. It's also a generalization of the standard definition due to Dedekind of the real numbers. The problem is with irrational numbers. Let's take, say, pi. What is pi? What object, shall we make that's there if you only know set theory, and that will serve as the number pi, 3.1415 and so on. Well, Dedekind's answer is to let pi be the section between all the rational numbers less than pi and all the rational numbers greater than pi. So you cut the rationals into 2 places at the point pi. So for instance, 3.14 is on the left set, and 3.141 is on the right set, and so on, and that's the definition of pi. Well, I came up with the things called the surreal numbers, in which the basic idea is you give me some numbers. A number will always mean surreal number. I just don't want to have to say it all the time. I didn't invent that term. Donald Knuth invented it. You put some numbers on the left and other numbers on the right. And as long as every number on the left is less than every number on the right, you have a new number. Okay? Well, let's take this case, where there are no numbers on the left and no numbers on the right. Well, then every number on the left is less than every number on the right, obviously. You don't have to check very much. There are no cases of this to be checked, it's true. You give me a counterexample, you'd have to produce a number here that wasn't less than a number here. Well, you can't even produce a number there, so it's true anyway. So that's my definition of 0. And then the definition of 1 is the simplest number greater than 0, which I get by putting 0 on the left and nothing at all on the right. And then the number 2, and you see this parallels von Neumann's construction. You put 0 and 1 on the left and nothing on the right. ... And if you always march towards the right, in other words, you never place any numbers on the right-hand side. You never say, I want it to be less than something. You only say, I want it to be more than something. Then you get the von Neumann ordinals. The parallelism being, whereas whenever von Neumann had a definition, I have the same definition, except that I don't put anything on the right. I have a slash and then there's nothing to the right of the slash. But now you can put things to the right of the slash. So for instance, what's the simplest number less than 0? Oh, well, that's -1. This is not a definition, it's a theorem, because you can define what addition means for these numbers, and 1 and added to -1 gives you 0. So -1 deserves its name. And so there's -2 as well. 0 and -1 go on the right and nothing goes on the left. So you get the negatives of the ordinals. But now you can ask what's the simplest number to the right of 0 on the left of 1, and you can probably guess what the answer is. It's a half. But it's not a half by convention or definition or anything. You can prove it's a half. You can prove that if you add this number to itself, you get 1. I haven't told you how to add yet, and I don't think I shall, but because life isn't long enough to tell you everything. And now in here, we can get all the rational numbers. For instance, okay, I'm going to invent this number. It's bigger than 0. Okay, I'll tell you that. Well, 1 is a number bigger than 0. Oh, but my number's less than 1. Well, 0/1, that's a half, is a number in there. Okay, but I'm going to tell you it's not equal to a half, by saying it's greater than a half. This number is 3/4, but I'm going to tell you my number is not 3/4 because I'm going to stick 3/4 on the right. And now I'm going to carry on doing this, alternately sticking things to the left and right. And it turns out that that's the definition of 2/3. Well, you can do other things. I can stick all the finite numbers on the left and omega on the right. The simplest number that's infinite, but smaller than the simplest infinite number. And that turns out to be omega minus 1. And again, these are theorems, not conventions. It's hard to convey it all very quickly. And then, we could do this up here, and then take omega and omega minus 1 and so on over here, and you get a half omega, which nobody defined, I think, before me in this connection. And you can do other things. You can have 0, 1, and so on, the same old finite numbers here, and omega over 2, omega over 4, omega over 8, which are easy to define. Turns out that's the square root of omega. And these things are called surreal numbers because they have a slightly bizarre aspect. I wrote a little book called On Numbers and Games, in which I found all these things. And they are like the real numbers in a sense. They are a field. They are, that is to say, you can add, subtract, multiply, and divide in them, except you can't divide by 0. And it's a totally ordered field. There's an order relation. Oh my, look at that money. And in a sense, it was at least influenced by von Neumann's definition of the ordinals. We're doing it two-sidedly. We have a sort of two-sided kind of set theory, but otherwise, so, if you only have one-sided set theory, you can only march in one direction. You march towards the right, and, then you get these ordinal numbers. But now you fill in all sorts of ways. We get additional numbers like 2/3 and pi and 1 over omega. And, oh, by the way, the number of surreal numbers is absolutely amazing. I've only written down a simple few of them. And those few have all been functions of omega, the first one. Well, that's because I can't convey the others to you. They're all over the place. It's extremely rich, an astonishingly full set of numbers. It's as if, you were hearing about the real numbers for the first time today, and you just knew about 0, 1, 2, and 3, the integers. Well, I'd tell you, well, there's a thing called a half, and 2/3, and so on, and then I'd introduce some irrational numbers. And, it takes quite a long time. You've already had that education, essentially. But you haven't had, I presume, any education about the surreal numbers. They're an extremely rich family. I went around in a permanent daydream after I discovered these things. Namely, I sort of... Well, there's this business about stout Cortes standing on the I don't know, some famous poem. He saw the Pacific stretched ahead of him. All the world was his or something. I don't remember. I had this feeling. I mean, here was this enormous world of numbers, and by the way, things called games as well, which were even richer. You know, I was lost in admiration of this thing. And every now and then, this other thought came, and you discovered it, John. Nobody knows about it, you know. That was really the most exciting thing in my mathematical life. Mind you, I have a pretty big ego anyway, but this really, was a case where nobody had seen it before. And I went around in a permanent daydream thinking how beautiful it was. And I think that was the major thing I thought. But certainly as well, and you discovered it, I mean, it's fantastic. It still brings tears to my eyes every now and then.
So, von Neumann and games.
Yeah, von Neumann. No, the game theory, my kind of game theory wasn't inspired by von Neumann. But it's interesting that von Neumann, invented a theory of games along with Morgenstern. Mrs. Morgenstern has, I think, just died. A few years ago, the Princeton University Press celebrated its 100th birthday. And they reprinted, they selected 100 best books over the period of its existence, one of which was the famous Theory of Games and Economic Behavior by von Neumann and Morgenstern. And anyway, Mrs. Morgenstern was still alive, and I had the sort of job of interviewing her delicately for things to say. I don't think in the end they used any of that. Another thing happened. There was this centenary celebration of von Neumann's birth a few years ago, and the Hungarian Academy of Sciences sort of organized a von Neumann year, and there were various academic celebrations in Hungary and so on. And but then they came to Princeton, and this was rather funny. There was the Hungarian ambassador and the cultural attaché and somebody else, distinguished-looking gentlemen with hats. They all had hats on, I remember. And the building in which von Neumann constructed his first computer, or at least his first computer was constructed, presumably by other people, is now the Institute Nursery School. And they were going to install a plaque. I was there as the von Neumann professor. It gets me into a number of things which are quite intriguing. I have no connection with von Neumann really, but anyway, these gentlemen came around, and the mayor of Princeton, a nice lady called Phyllis Marchand, was there, and there was a stone plaque with a relief head of von Neumann on it, and this was to be installed just outside the nursery school. And there was a little sort of set of curtains, so that at a suitable time you could pull the string, and von Neumann would be revealed in all his glory. But then it started to rain. This was timed for, say, 4:30, I think it was, or maybe 4. But it started to rain. And there was a little party of people, So in the end, we took shelter inside the nursery school. And there were all sorts of little kiddies running around with toys and tricycles and everything else. And then we stepped out briefly, and Phyllis Marchand made a little speech. The Hungarian ambassador made a speech, and somebody else made a speech, and then they pulled this string, and then we all got very quickly into a car and went away because the rain was getting quite heavy by then. But then we went away to the cemetery at Princeton, and where von Neumann's grave is, and nobody knew quite what to do there. So in the end, these 3 Hungarians all took off their hats and held them to their chests and looked down and muttered something in Hungarian or something, which may have been a prayer, I don't know. And then we went away from von Neumann's grave. Anyway, I learnt where von Neumann's grave was on that occasion. I'm sorry, I tend to produce an infinite stream. The best thing to do is to stop me, probably.
So was your free will theorem inspired by Neumann? Anything to do with statistical mechanics?
It is to do with statistical mechanics.
So can you tell us what is the free will?
What it is. But I don't think it's directly inspired by von Neumann. I mean, it's hard to say that. So let me say roughly what the free will theorem is. So I don't think it was determined at the beginning of the universe that I was going to throw that pen on the floor. Okay? I believe I have free will to a certain extent. I can take a decision, or let's say not even take a decision. I can do something, and that I can make a free act or do something that was not controlled, was not determined by the history of the universe up to that point. It's very difficult to say that that statement is true. Very difficult even to give an objective meaning to it. But most of us believe that we have free will. Now our theorem this is a theorem of that I proved with Simon Koshin, and I think he's the lead author in this, is that if we do indeed have free will, in the sense that our actions are not functions of the past history of the universe at the time they're made, what past means has to be gone into too, by the way, then so do elementary particles have free will, in the sense that their actions are not functions of the past history of the universe. Now, in some sense, the content or the main implications of this result have been known for a long time, but it's usually stated in a slightly different way, to say that quantum mechanics does not predict what a particle does. It's a non-predictive theory. That's a much weaker statement. Our theorem uses a few results from quantum mechanics, but only some very, very simple results. There's no doubt about what they mean. And of course it implies that quantum... Oh, by the way, the theorem then got strengthened. Neither quantum mechanics nor any extension of quantum mechanics can predict what a particle can do, and so on. Well, our theorem says more strongly that no correct theory can predict what a particle can do, basically because it hasn't decided yet. It takes a free action, which is not a function of the past. There's no way of taking past information and using it to decide what the particle will do, because it's not a function of the past. It's a rather subtle theorem to state and prove, but it's quite easy. And I can tell you very quickly what it's based on, the so-called Cauchy-Specker paradox, which is dates from 1965, essentially. I'm drawing on the surface of a cube a certain configuration of points, which basically consists of 9 points in a square array on each face, and then the midpoint of each edge. I'm not drawing it very accurately. But this altogether defines 33 lines through the center of the cube. You join the point I'm marking here to the center of the cube, and you get 33 lines that way. And there are things called spin-1 particles, and one property of spin 1 particles, you can interrogate them and you ask them a particular question, which is, what's your squared component of spin in this direction, you say? And the particle answers 0 or 1. Well, let's say it doesn't answer, of course, doesn't use those words, but it does something which we call 0, and it does something else which we call 1. And it doesn't very much matter what those things are. But it has this peculiar property that if you ask it questions in 3 orthogonal directions, it always tells you 2 1s and a 0. Now that's called measuring the squared component of spin in a given direction. That language is incorrect because it sort of assumes that there is something called the squared component of spin in a given direction. But there can't be, because according to this Cauchy-Specker paradox, there isn't a function of direction which takes the values 0 and 1 only, and for every 3 orthogonal directions takes 2 1s and a 0. You can't define such a function even on this set of 33 directions. That would mean you had to assign, you sort of think of asking the particle what it answers, and it says, I'm going to answer 0 if you ask me this question, and I'm going to answer 1 if you ask me this question, and so on. But you'll find, if you try and solve this little puzzle, that there's no solution to it. It's not possible to assign 0s and 1s to these 33 directions consistently with this 101 property. So the particle is, in a sense, doing what I did when I played 20 questions with my 2 older sisters when I was a boy. You probably know it under some name or other. You think of an object, and you've got to say whether it's animal, vegetable, mineral, or if you're sophisticated, if it's abstract. And then your sisters ask you questions about it. And each question has only 2 possible answers, and you've got to answer them. Well, when I used to play this game with my sisters, perhaps I should say my sisters used to play the game with me, I would change the object. If I sort of sensed that they were getting near to my object, I would change the object. Now you have to be quite a clever little boy to change the object, because you've got to think over the 7 questions they've asked so far and find another object that would give exactly the same answers. Well, let me tell you, if you want to play this with your big sisters, here's what you do. While they are trying to solve the puzzle, you are trying to solve the puzzle given their answers. And then this homes in on some object. You also try and home in on an object that's distinct from yours, so to speak. And then when suddenly you think, oh, they're getting too near, you can switch to your new object. However, it's hard to do that twice. That would mean carrying on 3 sort of things all at once. But anyway, I succeeded every now and then. The penalty for not succeeding was to have my ears bitten, which was rather painful, so I tried to succeed. But anyway, what I'm trying to say is particles do this. They don't have an idea for every possible question what they're going to answer. No. They just answer it in accordance with this 101 rule. They answer it, so to speak, on the fly. They can't have an idea what they do for every possible one of these 33 directions, because there isn't a consistent set of answers for these 33 directions. So that's the Cauchy-Specker paradox of roughly 1965. And what Cauchy and I did in proving the free will theorem was produce a twinned version of that. You can take 2 particles that are remotely separated and such that they will give the same answers if asked the same questions. This is a version of the EPR paradox, the famous Einstein-Podolsky-Rosen paradox, if any of you know it. you know, they give the same answers even if they're remotely separated, so that they can't transmit information to each other in accordance with the principle of relativity. It's as if I had a twin brother, which unfortunately I never did. I sort of dreamt of having a twin brother rather a lot. And we could be interrogated in separate rooms and had to agree on what our object was, you know, had to answer for the same object. It's much harder to change the object in that case, you know. If you've got a little toy radio or something, you know, the radio transmitter, you can speak to your twin brother and say, look, change to so-and-so. But if you're held incommunicado, and I'm sure my sisters would hold us incommunicado in those circumstances, you can't do that. But the particles actually do it. That's the most amazing thing. Well, numerous people have tried to explain that away in some sense. There are hidden variable theories, you know, in which you suppose that to suppose a hidden variable theory in this case is essentially to suppose that there is something which, you know, the spin in a given direction, the absolute spin in a given direction. But all of these hidden variable theories have sort of come a cropper against the sort of fundamental facts of physics. And often people have tried other explanations of how the world does it. Well, you don't need an explanation of how the world does it. It does. You know, this parallels what happened in Newtonian gravitation. How does the sun pull the Earth across 93 million miles of empty space? What kind of string is holding us to the sun, you know? Well, you don't need it. Newton was very clever. He said, hypotheses non fingo, except I'm pronouncing the word hypotheses as if it were English rather than Latin. I frame no hypotheses. And, you know, that was a very sensible thing to do. The analogous thing here is framing a hypothesis as to how the twinned particles do it. Does one of them transmit information to the other? Well, no, there's no need for that. The answers are related in a certain way. If you do ask them the same questions, you will get the same answers. Not because they're transmitting information from one to the other. That's not compatible with relativity theory. But because they do. They just give the same answer. We don't have to explain how they give the same answer. And many people are sort of caught up on this. They feel they have to provide an understanding of how nature does its tricks. Well, it's sufficient that it does its tricks. You know, there is no explanation. This comes, one consequence of our theorem is that there isn't a relativistically invariant mechanism for what's called collapse of the wave function or reduction. You can't do it in terms of functions of the past. You can't explain it in terms of its previous state. There's no such mechanism. The world doesn't work like that. It just works. How does it work? Oh, well, that's not a question to ask. I'd like to say that's an impious question. You know, it's not for us to understand how the world works. Yes.
So von Neumann, inspiring.
Yes, you know, I was never sort of conscious of von Neumann, really, but well, until I became the John von Neumann Distinguished Professor, because, how can I say it? And I don't think, you know, he exerted either a benign or a malign influence on me somehow, you know, ooh, think of this. But I was struck very much at this von Neumann meeting in Long Island that I mentioned, with the fact that there was a sort of superficial thing, namely, von Neumann worked in set theory and ordinal numbers. I wrote a thesis in set theory, and which was, I suppose, to some extent influenced by von Neumann. I knew about his definition of the ordinals, but I found the surreal numbers. But when I found the surreal numbers, I wasn't thinking of von Neumann. The life game, yes, it definitely came out of von Neumann, but I don't regard that as really work. I thought of it as a plaything, a hobby. Games, no, my kind of game theory is not remotely like von Neumann's, but it is game theory. Yeah, it's combinatorial instead of, well.
Number theory, algorithms,
Yeah.
automata, physics.
Yeah, but I mean, let's put it like this. Von Neumann worked in a tremendous number of different subjects, okay? So it's hard to avoid him. And I've played around with a number of different subjects too, but I don't think there's a real influence at play here. After I got this job at Princeton, let's say it gave me a soft spot for von Neumann. It's rather nice being called John von Neumann, Distinguished Professor of Mathematics at Princeton University. Let me say that again, the John von Neumann. But that's a soft spot, so to speak. I sort of feel in some vague way I have a personal relationship with him, but honestly I don't. I mean, but it makes me go along to these von Neumann meetings and so on. And it's rather nice. By the way, a rather funny thing happened, Americans have this idea that the English are all sort of reserved, There's a picture of going along in a railway carriage and we don't speak until, we've travelled 400 miles together or something. And then it's just, could you open the window a little bit? I've been boiling or something. But I find it totally the other way around. When I was in England, eventually I got made a professor. Now, professor means something in England. In the States, every tin pot little so-and-so is called professor something or other. But in the Cambridge math department, there were 3 professors out of, 60 or 70 teachers of mathematics I'm talking about. I eventually became one of these things in 1981, I think it was. And then I had a little dream. It was that I'd be crossing the road, and somebody would say, it was always a girl in the dream, would say, "Excuse me, Professor Conway," and people would look around to see what godlike figure was being addressed, That was my dream. It never happened once, I was really disappointed. And the only circumstance well, never mind, I won't say the only circumstance, well, I will. It was at sort of formal meetings where somebody agrees or disagrees with what Professor so-and-so said, But then I came to Princeton, and I got called Professor Conway all the time. I'm used to it now. Student sort of says, "Excuse me." I get this dream. Some of them are girls too. And I did not like it. It took me a long time to get used to because it sort of distanced me from the students, I'm sort of used to it now. Actually, there was a secretary in the department, or receptionist, I suppose she was really, who had it just right, Elaine. I would come into the mailroom in the morning, and if I came in alone, she'd say, "Hi, John." Okay, fine. But if I came in with somebody else she didn't know, she'd say, "Good morning, Professor Conway." Because, it might be somebody who needs impressing, That's really wonderful. She's left, unfortunately. Yeah. I'm sorry, we should stop.
No, that's absolutely fine. See, nobody's reading.
I used to say, it's hard to shut me up, as you might have deduced, but I used to say, if it sits down, I'll teach it. If it stands up, I'll carry on teaching it. But if it runs away, I might not be able to catch up. That's become very true now that I have to walk with a walking stick. And I reminded Sorin today of Groucho Marx's statement, which I think is terribly relevant to teaching. He said, I usually do this, well, never mind how I usually say it. He said something like, honesty and sincerity are two of the most important things in the world. So if you can fake them, you've got it made. I modify this slightly for teaching purposes. When you're teaching stuff, if you've taught it for years and years and years, it's hard not to get bored with it. I was teaching linear algebra yesterday morning. Well, God, I've been doing the same thing for donkey's years. So the thing is that enthusiasm is a most important thing. It's hard to be enthusiastic all the time yourself, but you must fake it. If you're teaching, don't let them know you're not enthusiastic. Fake it if you have to. And you probably will have to lots of times. But faking it is better than, letting it show that your enthusiasm is flagging.
So what do you do to keep it fresh? Do you try to prove new versions of the theorems? Or?
I don't know what I do. I fake it. I think. No, well, there's a way in which it's not.
Things on the fly to show how strong you are.
Oh yes, I do not use notes. But Napoleon had a good idea in that respect when he set up the École Polytechnique. Oh no, wait a minute. He revitalized it. I can't remember exactly which institution I'm telling you this about, but anyway, there had been a tradition of lecturing, often using assistants and using last year's lecture notes, which were themselves last year, the year before's lecture notes and so on. And Napoleon instituted a rule: you weren't allowed to lecture from notes, and you had to stand up. And that apparently revitalized the institution. That was a really wonderful thing. I don't know. I never used notes because I always lost them. And every now and then I've used notes. And then there's some theorem I can't damn well remember it. Or maybe I tried to remember it last time and I got into such a mess, I then try and write out the proof on a square piece of paper about 2 inches by 2 inches and stick it in my pocket. With any luck, the act of actually writing it out means it never comes out of the pocket. But, maybe it does if I can't quite remember. I'm not ashamed to, so to speak, to let it all hang out if, to let the students know I forgot this or something. But, yeah, I don't know. That reminds me of the division by 4 rule. Often I have grad students who are keen on getting jobs somewhere. And there are some things that they think that are just utterly wrong. The first thing is they think often that they mustn't let anybody see how easy my new theorem was to prove, and so if they see through that, I'll never get the job. They'd never think I'm doing deep mathematics or something, which I think is totally wrong. You should always make it as easy as you can for the students. Your job is not really to impress people. and the people who are hiring you or possibly hiring you are there to judge you as a teacher, not, not on. They don't give you marks for not understanding what you do. I think that's the basic idea. Nobody ever does. But then the other rule I say is the divide by 4 rule. Carefully write out what you're going to say, if you feel you must, and then divide it by 4. After you've written it all out, make sure it's divided by 4. And it doesn't matter if you repeat this a few times. It gets all the better if you divide it by 4 again and divide it by 4 again. Because if you actually say it, what you've divided by 4, people will understand it. And that's the most important thing, I think. I'm sorry, I didn't intend to go on giving deep philosophy.
We're really enjoying it. I have a question for you.
Yeah.
What do you think about all these papers and books in which the proofs are to perfectionism presented with no hint of how they are obtained, with the difficulty of struggling through a proof? How do you get ideas and so on?
Yeah.
I feel like teaching that part.
Well, there's something about this. Gauss's motto was pauca sed matura, few but mature. Or few but ripe is probably the way it's better translated. His philosophy was to write it to perfection. Euler is totally different, and he just sort of grabbed his pen and wrote out what the idea he'd had that morning.
Mistakes, though.
Yeah, with mistakes in and everything else. I think they're both good ways. I mean, why should we all let 100 flowers bloom was the Maoist doctrine. Why should we all teach the same way? I think it really is beautiful when you can produce the absolutely, perfect proof. Yeah. I wrote one paper which I decided to make as perfect as I possibly could. It's called The Characterization of Leach's Lattice. And I planned it. It's symmetrically written. It quotes the theorem to open the proof. It quotes the theorem to close the proof at the end. The style of it, I sort of worked on everything, not just the thing that was being said. And I thought I had the perfect paper. And then Sarah wrote to me that I had a little numerical calculation that went wrong. Oh, I mean, it doesn't matter a damn. But I sort of thought, this is my ideal. I was never going to write another perfect paper, by the way. One would have been enough, but I didn't quite get one because it had this mistake in it. But yeah. Yes, well, I am the closest thing that's been achieved to perfection, but I'm not quite there yet. Modesty is my only vice, and I'm working on the modesty aspect. So all of these jokes have been told thousands of times, so don't worry. They get to be better that way. Actually, that is a way in which, I used to be much in demand as a speaker, more serious usually than this sort of atmosphere, much in demand as a speaker on mathematics. And so I gave various talks lots of times. For instance, I spoke about the life game. I had a standard talk. And I must have given that talk perhaps 20 times, I don't know, but anyway, certainly at least 10. And I'm quite cynical about it. I mean, every now and then a joke comes up, totally extempore, a joke comes up, somebody laughs. Oh, that's in. From then on, this joke is there. And it always sounds as though it's just been invented, at least I hope it does. But it's not. I mean, yeah, I fake it. I mean, well, by the way, there was an awful time. Let me tell you, one time I was giving a talk in Montreal. I've forgotten what it was about. It doesn't matter what it was about. But anyway, it was to be videotaped. And this was in the days when that was quite uncommon. And the videotaper, you know, was due to arrive. And so anyway, I gave this lecture. Quite a big lecture, an audience of a few hundred or something, I don't know. And then at the end of it, they approached me. The man with the videotaping thing, you know, had only just arrived. Would I mind giving the talk again? Well, you know, this is terrible, because here were these jokes that were presented as if they just came up naturally, you know. And there were going to be some people in the audience who just heard them an hour before, you know. I said, okay, as long as only you, talking to my friend who, you know, knew some of my bad habits, as long as only you are in the repeat audience, you know, and you drag up a new audience of at least 5 people or something. So then I gave the same jokes, but even that, knowing that I had just told exactly the same joke an hour before, it's rather inhibiting. So don't let them do that to you. Yeah, I'm sorry.
Any questions from you guys? Advice for young generation?
I have a question. When you talk about the Old-Friedel theorem, in that context you said, you know, don't ask why
The world does it. Oh yeah. Yeah. It sounds a little counterintuitive, you know, generally, you know, it seems like this is the field of sciences that you ask how and why the world does it. Can you open a little bit that?
So why do I say don't ask? It's fine to ask, but don't expect an answer. I mean, why not? Well, I don't know. Nobody's ever found an answer in this case. That's something born of experience, so to speak. If the reason I'm advising you not to ask is because I know damn well you won't get an answer. It's hard to understand, you know. Listen, the situation is, here's a particle over here on Earth, say, and here's a particle on Mars. They have been experimented on and then separated, so they have a history, you know, a joint history in some sense. And now they promise to give the same answers. The laws of physics promise that for them, that they will give the same answers if you ask them the same questions. If you don't ask them the same questions, the bets are off, you know. Sorry, I'm trying to set the stage. And now you can prove by the Cauchy-Specker paradox that the answers are not determined ahead of time. Okay, that's a rigorous theorem. And so it's natural to suppose that, suppose I experiment on this one, I ask it a question, how can this particle know what it answered, if you understand me? There's not enough time for the information to travel. And indeed, it's not a question of limitation on the speed of information. I mean, if I ask this a question, I ask this, say, the same question, with you know, in a suitable intervals of time, it's meaningless to say which question came first, because in different frames of reference, either this could be first or this could be first. So it cannot be that one of the particles gives the answer on the fly and then tells the other particle what to answer. It just cannot be. So what happens? Well, it's perfectly consistent with relativity theory and quantum mechanics and everything else for there to be a law of physics that says they will give the same answer. It's not consistent with those for that answer to be determined ahead of time. So how can you know, I don't know, people have tried to invent mechanisms for it, but you can't have a mechanism because it's not determined, it's free. These answers are freely given but related.
So it's like an uncertainty principle. You can prove that you cannot. Imagine is the world before the electromagnetic field around the Earth discovered. Do you think that's what is missing? Something that will be discovered later?
No, there's nothing to be discovered. I mean, you know, this is what happens. Let's go back to this Newtonian business. Do you think that, let me ask this in, say, 1750. Do you think we have, you know, that the elastic, the nature of the elastic that pulls the Earth towards the sun, will be learnt in future years? Well, it won't, you see. Why is there some elastic? There isn't some elastic. The fact is that, you know, the Earth and Sun attract each other, and there's no elastic. There's no mechanism. You know, Newton was accused of occultism by his scientific colleagues at the time, you know, for not proposing a mechanism. But he was very much more sensible than they were. He framed no hypotheses. What we say, and it's not us, I mean, this is really what physics says, is that these answers in certain conditions will be the same, but not for any reason. That's just a law of physics, that they will be the same. And it's like it's analogous in this respect to Newtonian gravitation, only a few hundred years later. That assertion that they will give the same answers if asked the same questions, that assertion is consistent with relativity and quantum mechanics. No mechanism for arranging that will be the case is consistent with relativity and quantum mechanics. There doesn't have to be an explanation. So, I mean, this is one of those things. We're accustomed to explanations being discovered at some later date, but in this case, it's unwise to believe that there's an explanation at all.
Unless we replace quantum mechanics by something else, the next clue.
Yeah, but you see, no, that won't work. Well, let me explain why it works. We don't need much of quantum mechanics and to prove this theorem, and what we use is robust. The quantum mechanics does not have to be exactly true. It only has to be sufficiently closely true for the axioms we use to be true. And that sufficient closeness is already verified. Perhaps that's a little bit more than the truth, but never mind. I think that's the best way to say it. It's not a question of the present theory not being good enough to say how it will happen. No theory will be good enough to say how it will happen if it's correct. You see, I mean, what do you predict I'm going to do with this book? Am I going to drop it or carefully put it down?
Not give it to me because you the only copy you have.
Yeah, okay, but I asked you a specific question. Am I going to drop it or am I going to put it carefully down? If you tell me what I'm going to do, I'll do the other one. You cannot predict it. I'm a free agent. The particles are free agents. That's the reason why you can't predict what they're going to do. Not that, you know, what they do is not a function of the past. What I do with this book is not a function of the past. You know, we all have this feeling, I suppose, that we are not automata. I don't know, maybe some of you feel you are automata. But you know, we tend to act, at any rate, as though we thought we had free will. There's nothing inconsistent with supposing we do have free will. But if we do have free will, then the particles already have a certain small measure of it. Now, that's, by the way, it's very interesting. Philosophical discussions of free will are usually concerned with things like moral responsibility. That complicates it all enormously. But suppose I just take two actions, A or B, where nobody will die if I do one rather than the other, and so on. You know, they're inconsequential, so to speak. Then I believe I'm usually free to do A rather than B, or B rather than A, whatever it is. And if I have that kind of freedom, so do particles.
So I think when most people think of free will, they think of macroscopic actions with macroscopic consequences.
Yeah.
And a lot of the things that we observe macroscopically, to a large extent, behave deterministically.
Yeah.
I think this result that applies to these fundamental particles really has implications to our concept of this macroscopic.
Well, yes. Let's point out that we ask a particle a question in a microscopic way, essentially, but then we observe it in the end. There's a pointer on the screen which goes this way or something after it's been much magnified. So this microscopic decision that the particle makes can be sort of elevated into a macroscopic one or amplified into a macroscopic one. Now, I believe, it's a very natural belief, but it's got nothing to do with the free will theorem, which is a theorem, not just a belief. I believe that where we obtain our free will is a sort of amplification of certain decisions, not quite an amplification, I'll tell you what I mean later, of certain free decisions, as it were, or free actions of the particles in my brain. Let's discuss it. You see, there is a general theorem that you pass to the classical limit. Roughly speaking, if you have enough particles and they're behaving in a statistically random manner, then that basically means you get classical mechanics out of it. So in this book, this particle, I'm absolutely sure that some particle here is taking a free decision, right now, and it may say take a decision to jump up a little bit. Now, if they all took a decision to jump up, the whole book would jump, but no, that doesn't happen because there's some particle next door to it that takes the decision in the end. And if these are taking decisions to which statistics applies, which does not mean that they're random, by the way, but to which statistics applies, then if there are n particles here, they'll cancel out to within root n. Now, I don't know what n is here, but this means that in practice the cancellation is almost perfect, So this behaves like a dead book, I usually think of a stone when I think of it. It's full of life inside in the sense that the particles are all doing their own thing, but we don't observe anything. That's actually a provable theorem too, the passage from the microscopic behavior of the particles to the macroscopic behavior of the macroscopic object. So, and the way the sun and the earth and so on, they behave is governed by quantum mechanics, but in this case, that quantum mechanics averages out to classical mechanics, But now, let me repeat what I was saying about the brain, but with extra precision. I talked about amplification. I don't think there's any amplification. What I think happened, well, maybe there is, but what I'm saying is, in the brain, evolution has presumably designed for us some way in which this washout doesn't happen. That instead of all averaging out to essentially zero, it's arranged that there isn't complete cancellation. And then, somehow that is analogous to amplification. It is not de-amplified, and I'm sure we get our own free will from the free will of the particles inside us. However, that's just a belief. I mean, there's no sense in which I can hope to. I don't know what goes on in brains. Brains are complicated things. I can prove things about single particles, and that's rather different. So there's no hope, I think, at the moment of getting, any substance behind that feeling. But at least it's a plausible thing. It's a reasonable thing. Particles have free will. Humans have free will. Probably one comes from the other. But of course I don't know how. It'll be very subtle to do that.
So for Neumann, his book, The Computer and the Brain, as you said, he's everywhere, so you cannot avoid him.
Yeah.
He has a conjecture that the brain doesn't work with big numbers because somehow from all the automata theory interpretation of the brain, there is no mechanism for correcting for rounding errors.
Yeah.
So therefore, it's very parallel with many things in parallel, but with no big numbers, which is a very interesting thing.
Yeah, no, I think von Neumann was a clever guy, there's no doubt about it. I mean, he thought all sorts of things. I was thinking of something else that just came to me from what you said then, but I've lost it. I had a sort of love-hate relationship with quantum mechanics. At Cambridge, where I studied, I did quantum mechanics. I did in some sense, and it put me off, that kind of physics, because I felt I couldn't understand it, and I never would, you know. Incidentally, I took courses in QM from Dirac, among others. But, you know, I never felt I understood a damn thing. And then I used to read articles every now and then in the Scientific American, still never, in a vague hope of understanding something finally. But my friend Simon Koshin, who is the co-author in the free will theorem and also co-author with Specker of the Cauchy-Specker paradox, which is what preceded it, he started talking to me about certain geometrical problems coming from QM. And I got a glimmering of an understanding of QM. And by the way, I used to believe that there had to be a mechanism for collapse and all this sort of stuff. I was a hidden variable theorist I would have been if I had any competence in the subject at all, which I didn't. Now I sort of feel I understand one thing about quantum mechanics. You know the story, I know who is it? I think it's Dorothy Parker. I know two things about the horse, and one of them is rather coarse. Well, I only understand one thing about quantum mechanics. I don't know whether it's rather coarse or not. It's rather subtle, actually. Yeah. Yes, well, you know, this kind of talk ought to happen in a bar late at night.
Well, it's a bar with big whiteboard. Well, thank you so much. Not much, it was just a piece of bagel, so you did pretty well. Thank you so much. Wonderful.